Hi, I am Adriana and I'm going to explain task 1 that consists of 5 parts which focus on the continuous random variables of x and y. Before we move to the solution part, we need to obtain the joint probability density function. So let fxy equals to xy over 2, where 0 is less than y, less than x, and less than 2. Otherwise, the function will be 0. Part A, it asks to show that the joint PDF satisfy the properties of being PDF. First, we check non-negativity. If we sketch the graph, we can see that the graph is lying on quadrant 1, which means all real values of x and y are positive. That means the joint PDF also positive.
Second, we check whether total area equals 1 or not. If we perform double integration by substituting the limit, we can see that the answer will be 1. Therefore, we know that the joint PDF satisfies the properties of being PDF.
Next, we move to part B where we need to find the marginal of x and y. If we perform integration with respect to y will be eliminated, leaving the function in terms of x only. So the marginal of x will be x cubed over 4, where 0 is less than x and less than 2. If we want to find the marginal of y, we need to make sure the function in terms of y only. So we need to eliminate variable x by perform integration with respect to x. So the marginal of y will be y minus y cubed over 4 and 0 less than y and less than 2. In this part, we also need to show that both of the marginals satisfy the properties of being PDF. If we check the non-negativity, both marginal x and y are positive everywhere. Then we continue to the second properties, total area equals 1. If we integrate gx with respect to x, we will get 1. Next, evaluate the integral of marginal y will also get 1. Thus, both marginal of x and y satisfy the properties of being a PDF. Continue to part C. If we substitute the joint PDF and marginal of y into the conditional PDF of x given y, we will get 2x over 4 minus y squared. Evaluate at y equals 1, we will get the conditional PDF x given y equals 1 is 2x over 3. So at x greater than 1.5, if we perform the integration where the lower limit is 1.5 and the upper limit is 2, we will get the answer is 7 over 12. In this part, we want to find the expected value and the variance of the conditional function. The expected value of x given y is when we integrate x multiplied with conditional function, and if we substitute the limit and evaluating the integral, we will get the expected value x given y is equals to 2 in bracket 8 minus y cubed over 3 in bracket 4 minus y squared. Before we proceed to find the variance of the conditional function, we need to compute expected value of x squared given y first. This is equals to the integration of x squared multiplied with the conditional function. If we substitute the limit and evaluate the integral, we will get ex squared given y is 16 minus y power 4 over 2 in bracket 4 minus y squared.
Now, we can compute the variance by substituting ex given y and ex squared given y to the variance formula, which is var x given y equals to ex squared given y minus ex squared given y squared. So we will get variance of x given y is equals to the 4 plus y squared over 2 minus open bracket 2 in bracket 8 minus y cubed over 3 in bracket 4 minus y squared close bracket power of 2. If we evaluate at y equals to 1, the variance of x given y equals to 1 will be 13 over 162. The last part in this task is to find function uv by using method of transformation. First step is we need to find the inverse. So we let u equal x and v equals 2x plus y. And then we express the original variables. So x equals u, y equals v minus 2u. Second step is we need to find the Jacobian. The Jacobian is actually when we differentiate x in terms of u and v, also differentiate y in terms of v and u. So we will get the Jacobian is 1. The third step, we transform the joint PDF to get function uv. If we substitute x equals u and y equals v minus 2u into the original function fxy equals xy over 2, we will get the function uv is uv over 2 minus u squared. The last step to get the transform function uv is determine new limits. We transform the original boundaries in terms of u and v. Therefore, the final joint PDF will be uv over 2 minus u squared, where u is between 0 and 2, and 2u is less than v and less than 3u. Otherwise, the function uv will be 0.
Hi everyone, my name is Emmeline Owijon. Today I will be presenting Task 2. For Task 2, we were required to create a discrete bivariate scenario. This involves defining two random variables x and y, constructing a joint probability mass function table, and finally calculating the covariance and correlation to analyze the relationship between these two variables. Our scenario focuses on the selection of a subcommittee at a university faculty. We are choosing 2 members at random from a group of 8 staff volunteers to recreate our bivariate distribution. We have categorized the volunteers into 3 groups, which is 3 engineers, 2 accountants, and 3 managers. In this scenario, we define our discrete random variables as x is the number of engineers selected and y is the number of accountants selected. Since we are only picking 2 people, if we pick one of each, x is 1 and y is 1. And if we pick 2 engineers, x becomes 2 and y is 0. If we pick 2 managers, both x and y will be 0. So, in this table, it illustrates the mapping of our sample space. There are 6 possible categories of selection. For instance, selecting 2 managers results in the coordinate 0, 0, while selecting 2 accountants result in 0, 2. Through this mapping, we identify that the possible values for both x and y are the set 0, 1, and 2. Based on the 28 total combinations possible, when choosing 2 from 8, we tabulated the joint probability mass function. Each cell represents the probability of that specific intersection of x and y. We have also included the marginal probabilities, px and py, in the outer rows and columns, which we will use for our upcoming calculations. To ensure our distribution is mathematically valid, we perform a verification. First, all values in the table are non-negative. Second, as you can see by the summation here, the sum of every joint probabilities equals exactly 1. This confirms that our function satisfies the requirements of joint PMF. So, for step 1, to find the covariance, we first need the expected values for x, which is the number of engineers. We multiply each possible value of x by its marginal probability. This gives us an expected value or mean of 0.75. So, next, for step 2, we repeat this for y, the accountants, finding a mean of 0.5. In step 3, we calculate the joint expectation EXY by multiply each x and y pair with its corresponding joint probability. The only non-zero product comes from the case where 1 engineer and 1 accountant are selected, resulting in 0.2143. Okay, then by substituting these values into the covariance formula, we get a result of negative 0.1607. The negative value indicates an inverse relationship. Mathematically, this means that selecting an engineer reduces the position available for an accountant within our fixed sample size of 2. Now, we calculate the correlation. We begin by finding the variance of x. We first find EX squared to be 0.9643, and after subtracting the squared mean, we find a variance of 0.4018. Taking the square root gives us a standard deviation of 0.6339 for the engineers. Following the same steps for variable y, we calculate its variance as 0.3214. This results in a standard deviation of 0.5669 for the number of accountants selected. Finally, we divide the covariance by the product of the two standard deviation to find the correlation coefficient R, which is negative 0.4473. This indicates a moderate negative linear relationship. It is not a perfect negative one because the managers in our pool act as a third variable, allowing for outcomes where both engineers and accountants are not selected.
Hi, I'm Ankit. For this segment of the presentation, I will be walking you through task 3, which focus on the mechanics of moment generating functions. Our objective is broken down into 4 main steps. First, we will select a baseline probability distribution for a single random variable x, derive its moment generating function, and extract its means and variance. Next, we introduce a second variable y and scale our model up to the bivariate case to find their joint moment generating function. Finally, we will use that joint function to extract the marginal moment and formally compute the covariance between x and y. We have chosen the bivariate normal distribution as our foundation for this task. Let's dive straight into part A and set up our univariate model. Hi, I'm Ankit. For this segment of the presentation, I will be walking you through task 3, which focus on the mechanics of moment generating functions. Our objective is broken down into 4 main steps. First, we will select a baseline probability distribution part A by defining our random variable x as a normal distribution with mean mu and variance sigma square. To find the moment generating function, we apply the standard expectation operators to e power of tx. This gives us our starting integral over the real entire line. The challenge now is to combine these exponential terms and solve the integral. We begin part A by defining our random variable x as a normal distribution with mean mu and variance sigma square. To find the moment generating to integrate this, we need to manipulate the exponent. We first combine the term over a common denominators. The critical step is completing a square with respect to x. By expanding and regrouping, we successfully separate the exponent into two distinct parts: a new quadratic term involving x and a constant term that only depends on our parameter and t, which we can eventually pull out of the integral entirely. When we substitute our expanded exponent back into the main equation, we factor the constant terms out of the front. Look at the remaining integral. It perfectly matches the structure of a normal probability density function and just a shift mean of mu plus sigma square t. Since the area under any valid PDF must integrate to exactly 1, the entire integral evaluates to 1, leaving us our clean, closed-form moment-generating function. When we substitute our expanded exponent back into the main equation, we factor the constant terms out of the front. Look at the remaining integral. Finally, we extract our moments, taking the first derivative of the MGF and evaluating it at t equals to 0, immediately recover our means. Applying the product rule for the second derivative gives us our second raw moment. Using the standard variance formula, expected of x squared minus expected of x squared, the u squared terms cancel out beautifully, confirming our variance is precisely sigma squared. This derivation confirms that the internal consistency of the normal distribution parameters. Moving to part B, we expand our scope to two random variables, x and y, which follow a bivariate normal distribution and are linked by a correlation coefficient rho. We begin with the foundational definition of the joint moment generating function. However, instead of attempting to solve a high complex double integral over the joint probability density function, we are going to use structural properties of normal distribution to bypass the heavy calculus entirely. The key mathematical trick here relies on a fundamental property. Any linear combination of jointly normal random variables is itself a normal random variable. By treating our constants t1 and t2 as coefficients, we define a new variable z. We then calculate the mean m and the variance v squared of this new variable. Notice that the variance equation explicitly captures the covariance between x and y through the correlation term. Because z is just a single normal random variable, finding our joint MGF is now as simple as evaluating the expected value of e power of z. We can directly recycle our proven result from part A, plugging in for the argument, and by substituting our expression for m and v squared back into the exponential, we arrive to our final joint moment generating function. I want to draw your attention specifically to the final cross term containing rho. This is structural signature of dependence that we will rely on in the upcoming covariance calculation. In part C, our goal is to extract the individual means and variance from our newly derived joint moment generating function. The general rule for a bivariate MGF is to take the partial derivative. To find the mean of x, we take the first partial derivative with respect to t1. By applying the chain rule, we pull down the t1 coefficient from the exponent. When we evaluate this at t1 equals to 0 and t2 equals to 0, the t term vanish and the MGF term becomes 1. And we left perfectly with mu1. By symmetry, differentiating with respect to t2 gives us mu2, which is for the mean of y. To find the variance, we need the second raw moment. We take our previous first derivative and differentiate it again with respect to t1. Because t1 appear in both of the coefficient bracket and the MGF exponent, we must use the product rules. Evaluating this massive expression at 0, 0, simplify elegantly down to sigma 1 squared plus mu1 squared. Using our standard variance definition, we subtract the square means, leaving us with exactly sigma 1 squared. The exact same logic applies to y, yielding sigma 2 squared. This successfully proved that the joint MGF perfectly preserves the marginal parameters of both individual distributions. For our final task, we need to find the covariance between x and y. We start with the classical definition of covariance. From part C, we already know that the product of our marginal means is simply mu1 times mu2. Therefore, our entire objective boils down to finding the joint expected x, y. Using the moment generating function approach, we find this by taking the mixed partial derivative, differentiating first with respect to t1 and then with respect to t2. We take our first derivative from the previous section and differentiate it again this time with respect to t2. Because t2 appear in both the linear coefficient bracket and up in the exponent of the MGF itself, we must apply the product rule. The derivative of the bracket isolates the rho, sigma 1, and sigma 2 term. The second half of the product rule pulls down a symmetry bracket containing the t2 coefficient. By evaluating our mixed derivative at t1 equals to 0 and t2 equals to 0, all the variable terms vanish. Since mxy00 is equal to 1, we are left with exactly rho sigma 1, sigma 2, plus mu1, mu2. We take our first derivative from the previous section and differentiate it again this time with respect to t2. because T2 appear in both the linear coefficient bracket and up in the exponent of the MGF. Finally, we plug this joint expectation back into our starting covariance formula. The mu1, mu2 terms cancel out perfectly. We are left with a covariance of rho sigma 1, sigma 2. This result perfectly validates the internal consistency of the MGF framework and is reconstruct the standard textbook definition of the correlation coefficient.